Hi, this is Hake. I am covering a BCS Unit 6 in which last point, that is a design of downlink. In a satellite communication, all of you know that meaning of uplink and downlink. The communication between transmitter and satellite is known as a uplink, and communication between satellite and earth station, that is receiver, is known as a downlink. Today we are going to cover a downlink. In a satellite communication, designing of downlink is very important. By using the design of downlink, we can calculate signal to noise ratio, that is S by N, carrier to noise ratio, that is C by N, and we can calculate the G by T ratio for our simplicity. Consider a simple structure of a downlink, that is upper part is a satellite, lower part is a receiver. In between a satellite and receiver, the free space are available. Actually, in our first lecture, we have designed link equation. The link equation and downlink equation both are same. Only here we will derive the downlink equation in step by step. Here, satellite antenna transmit the electromagnetic signal towards a receiver side. So here, satellite act as a transmitter and base station act as a receiver. Satellite antenna is a directional antenna. It radiates its power towards a receiver side. So, at the receiver, total received power is denoted by PR, which is equals to PT, that is a total transmitted power, into the gain of the satellite antenna into gain of the receiving antenna divided by path loss. Here, path loss is nothing but 4 pi into r divided by lambda bracket square. R is a distance between a satellite and earth station, and lambda is a wavelength according to the operating frequency. This formula can be right in terms of the EIRP. So, received power PR is equals to EIRP into gain of the receiver antenna divided by LP, because all of you know that what do you mean by EIRP and how to calculate EIRP. What do you mean by LP and how to calculate LP. Above formula we can write in terms of a dB also. So received power in terms of dB is equals to EIRP in dB plus gain of the receiver antenna in dB minus path loss in dB. If we check a downlink block diagram of figure in which you see carefully there are many losses in a system. First loss is a antenna loss, antenna, satellite antenna. Second is a path loss. Third is a atmospheric loss, and fourth is a receiver antenna loss. So we will consider the all losses in our design, and hence your final design equation for received power is equals to EIRP in dB plus gain of the receiver antenna in dB minus path loss in dB minus atmospheric loss in dB minus antenna transmitter loss in dB minus receiving antenna loss in dB. This is a final received power formula. Now I told you कि downlink design of downlink is used to calculate the C by N ratio and G by T ratio. But in a C by N ratio, C is nothing but a received power, that is PR, but N is nothing but a noise power, that is Pn. So noise power Pn is equals to K into T into Bn. K is a Boltzmann constant, T is a source temperature, or it is also known as a system noise temperature, and Bn is nothing but a noise bandwidth. So C by N we can denote as a PR by Pn. If we put the value of PR and Pn in a given equation, we will get a final formula. And which is nothing but C by N is equals to EIRP in dB, path loss in dB, atmospheric loss in dB, transmitting antenna loss in dB, receiving antenna loss in dB, plus G by T ratio in dB or in terms of normal minus Boltzmann constant in dB minus noise bandwidth in dB. This is a final formula for calculating a C by N ratio, or we can use a same formula to calculate a G by T ratio. Okay. But sometimes we can use this formula to calculate a C by N ratio in terms of carrier to noise power density ratio. Carrier to noise power density ratio. So first of all, understand what do you mean by noise density, and then we'll find out the carrier to noise power density ratio. Noise density is denoted by N naught. It is the ratio of noise power to the spectral bandwidth. Noise density is denoted by N naught, which is equals to noise power means Pn divided by spectral bandwidth, or we can say noise bandwidth means B, and hence BB get cancelled and your final formula for noise density is equals to K into Ts. K is a Boltzmann constant and Ts is a system noise temperature. If we put N naught in a above equation, that is carrier to noise power density ratio, so we will get a finalized formula, and this formula is denoted by C by N naught. N naught means power density. Only the one term will cancel, that is a B, noise bandwidth. Remaining formula is same. So by using a downlink design, we can calculate a carrier to noise ratio and G by T ratio. Hence we can say design of downlink and design of uplink are used to determine the C by N ratio and G by T ratio. Thank you.